I'm going to do the recording. So number 11 here on page 40, the 2010 U.S. Census indicated the true proportion of Americans that were female was actually 50.8%. All right, so calling back to the problem on page 37, the statement was that it was a 50-50 relationship, males and females, that you had a 50% of the population or 50% chance of being a male and 50% chance of being a female. That's not necessarily the breakdown. Honestly, I do tend to go off on tangents, as you may have noticed throughout the course, but sometimes, and in this case, I hope that it's one of those cases, they tend to be relevant. I was watching Jurassic Park. I got sucked in. You know, like when you get sucked into a marathon, you get sucked in like for the whole day, as most of you probably know, if you're TV or movie people. So I got sucked in, first Jurassic Park, and then after that, you know, The Lost World, Jurassic Park 3, and all that. Terrible movies. The first one was great. The ones after that, then the Jurassic World, and then Fallen Kingdom. But there was a scene in the first Jurassic Park that talked about how all of the dinosaurs on the island were female and therefore could not procreate. Right? And so, like, there were no males. So it was 100% females. And then they came across some eggs and that hatched. And they said, well, wait a minute, what's going on here? And in order to recreate the dinosaurs, I mean, if anybody's seen this movie, I'm just kind of rehashing old history. But if anybody's seen the movie, you remember that they didn't have pure dinosaur DNA, so they had to splice together DNA from different creatures. And one of it was I believe, a West African frog. And apparently that particular frog, based off of its own genetic history, has the ability to switch genders. If one gender is overly dominant in a particular area, it'll switch, like a certain proportion of those frogs will switch gender. Right? And males become females and so on. So I'm not saying that's what happened with Americans, but I'm saying that if you wanted to apply this information, this type of study to something other than humans, then you're not just limited to necessarily a 50-50 relationship. You know what I'm saying? So when you're looking at, for example, forgive me if I'm wrong, I believe there were West African tree frogs, but I'm not 100% sure. I just know that there is a species of animal out there that is capable of changing gender. Now, that being said, my sole knowledge of this particular species comes from the movie Jurassic Park, which is fiction. So it could be completely made up. So take it with a grain of salt. But the idea that we would move away from something that's just 50% male, 50% female is not something that's absurd. It's possible, just maybe not always when we're dealing with humans. All right, so we want to use this information to create a new probability distribution for the gender selection technique question from page. Oh, there's a typo for somebody. I believe it was page 37. Yeah, it was page 37. So, then graph the distribution, and we want to know, is it still approximately normal? All right, so we want to dive into this scenario here. Well, there's a few different ways that we can do this. One way would actually be to put in the entire distribution into the binomial formula and go from there. That could be pretty time consuming. Desmos is a really valuable resource, as we know. It's one of those resources that you kind of look at as being, I'd love to be able to use it if only I knew how to use it. You know, it's sort of like that idea. All right, so I'm going to give you a quick little refresher on how to use the binomial probability calculator on Desmos to be able to help you do this sort of work. All right. So first thing you're going to do, and I'm going to stop this share. I'll pause, stop the share. All right. So we're in the binomial probability calculator. This question is saying that we have 14 births. All right. So the number of trials, and I'll go back to the notes in a couple of seconds, but we can actually kind of set things up right away, right here. All right. But we have 14 births. So the n value is going to be 14. Right? Because that's what they're asking. Is it unusual to have 11 girls among 14 births? So I can make this n value equal to 14. So I drag the slider over to 14. If it's too much trouble, then just click right into the field and it does the job for you. Probability, the p-value, probability of success is 50.8. So the p-value is really 0.508. I'm just writing it down as we go. So if you can get it to scroll to 0.508, more power to you, but you see that it only goes in half percent increments. So what you would have to do here is actually click into the P field and type in 0.508. All right. So these two numbers, the N and P, define the probability distribution, right? Which is good. It's actually surprisingly good, because what that tells us is, or it gives us anyway, is the shape of the distribution, right? That shape is approximately normal, right? So in the question, it says graph the distribution. We have the graph. Is it approximately normal? Yeah. All right, so we have that information. And so what I tend to do is as I change a calculator, I save it so as a new name, so that I have it specific to a problem that I'm working on. So I would say like binomial probability page 40, number 11, something like that. Duplicate the graph. So any changes that I make here, they would be specific to that problem, but they wouldn't change my original calculator, the one that's stored on Blackboard. I'll always have a fresh calculator to work off of there. All right, so let me pause again. All right, so I have it all in my iPad. I saved it, I ported it over, it's good to go. So we have an approximately normal distribution. We're good to go there. It looks roughly bell-shaped, so that's our indicator. Right? We don't have to do an empirical rule test. It's just a visual identification. And when I say graph the distribution, and I'll be very clear about this on the test, I'm not actually looking for you to hand draw anything. If anything, I'm looking for a Desmos submission. Right? I mean, you're welcome to hand draw graphs, but it's definitely not necessary. So it's got a little out of whack. So, anyway. So we have the picture. Now I need some numbers, right? I need these values, P of X for 0, for 1, for 2, and so on, right? So if I could, what I would do is just tap on these values and see what it would give me. And I can. The issue that I might run into is clutter. It tends to be kind of a mess. I mean, it gets pretty wonky. But also rounding. You just got to make sure that the rounding is up to snuff. So I'm going to show you a couple of ways to do it. So if you can do it that way, do it that way, as long as you get what you need out of it. And by that, I mean the rounding, and you're not overwhelmed by the organizational piece, right? What I tend to do is just kind of zoom in a little bit so it's easy with my fat fingers to not tap on the wrong thing. So I tapped on the first point. I'm looking for the y values corresponding with the x value. Right, so the x value of 0 corresponds with the y value of 0. So my first entry is 0. Right, it's a little on the thick side. All right, so tap in an empty space. Don't tap on another point, because if you start tapping on points simultaneously, that's when it gets cluttered. So here I'm looking at it, it's 0.0007. That's not an acceptable amount of accuracy. I need at least 3 significant digits. All right, so I'm gonna have to come back to that one. I'm gonna see if I can get values that at least give me 3 significant digits. Like for example, 3 gives me 0.0195. That's fine. After the zero, you start off with the decimal point. Ignore the zeros. You start counting decimal places after the zeros end. That's how you determine whether you have 3 significant digits. Yeah, the 0.508 came from the 50.8. Exactly. Very good. Okay. So I'm going to, again, tap in an open space here to turn that off. Grab the next one. 4 gives me 0.0554. That's fine. That's 3 significant. Tap in an open space or tap on the point a second time. It'll turn it off. 0.114 is fine. That's for 5. For 6, 0.177. If you want to put the 2 in, that's fine. I'll never take off points for you putting more decimal values than are necessary. It's when you put too few, that's when you have a problem. All right. All right, so that was 6, 7.209, 8.189, 9. You see 9 is over rounded. It's only 2 decimal places. It's only 2 significant, so I got to come back to that one. 10 is fine, 0.0671. 11, 0.0252. We'll turn these off. 12 over rounded, 13 over rounded, 14 over rounded. All right, so I'll come back to those. And what do I mean by coming back to them? Well, I can't just tap on it again and hope for the best. I mean, the one that I was willing to accept was 0 because 0 is 0 regardless. So I'm not worried about that one. But the first value that I care about here is 0.0007. I want to see if there's a way of getting more decimal values out of that. Right. So what I want is the probability of getting exactly a 1. Right. Using the binomial probability technique, can I get exactly a 1? Right. So you see here the A value is minimum number of successes, the B value is the maximum number of successes. If I want exact cases, I just make the mins and the maxims the same. So what I would do here is just make this a 1, the A value, and make the B value also a 1, and see what that gives me as I scroll down for a probability. And you can see under binomial distribution, where N and P are the trials and success probability, you can see now that 3 significant digits is a little bit more than the 0.0007. It would actually be 0.000704. Right. So what I did was I used the graph to my advantage to get the bulk of the table completed, but now I'm just going back and getting the more challenging ones. All right. So 2, still better than having to do it by hand. So looking for 2, I get 0.00472. Then I need 9. So I'm going to scroll up to 9. And again, if you have trouble landing on the number when you're sliding, just type it in. All right, 9 gives me, well, that one actually gave me a 0.13. If I rounded to 3 significant, it would be 0.130. So that one I could have grabbed, but I didn't know. I didn't know going in, so I had to check it. 12. 0.00651. 00651. 13. 0.00103. And for 14, 0.0000762. All right, so a little bit more accuracy than maybe we would have had otherwise. Right, and it's a necessity. Right, we need to have that amount of accuracy in order to be as accurate as possible. I mean, it's the dumbest thing that I've probably said all day. Like, yeah, we need to have that accuracy in order to be accurate. But yeah, that's pretty much it. Otherwise, we have an unacceptable amount of error that'll throw our computations and conclusions off. Right. So now we got to do something with this. Because they're asking, is it unusual? So we have the binomial distribution. Now I need to make a determination of whether it's unusual to get 11 girls among 14 births. Now, I would say common sense wise, just looking at the probability, it kind of looks like it would be unusual. I mean, it's very small probability. It's about 3%. So my gut's telling me it's going to be unusual, but we need to verify using the appropriate rule. Yes, N is 14 because of the number of births. So whatever the total number of trials would be. So in this case, trials is the number of births. Exactly. That's a good question. Yeah. So generally what's going to happen is you're going to have two numbers. You know, the value that represents the number of attempts. And then the value that represents the number of successes. The number of attempts or the number of trials, that's your N value. The number of successes, that's your X value. The 0.508 came from the problem. It was given. It said the true proportion based off of this information that of Americans that were female were actually 50.8%. So that gave us the 0.508. Right. The previous problem had it at 50-50. This one is a variation of that. No problem. So we need to compute mu plus or minus NP, not mu plus or minus NP, geez Louise. Mu plus or minus 2 sigma. All right. I'm writing like super tiny for some reason. I have no idea why. Right. So mu plus or minus 2 sigma. Now, because it's binomial, and this is a big component, because it's binomial, we can use the rules that tell us that mu is equal to NP. That's where when I accidentally stumbled and said NP before, that's what I was thinking. Sigma is equal to the square root of NPQ, or NP times 1 minus P. I'll write it out here. Very important, the 4 conditions necessary for a distribution to be considered binomial need to be satisfied, right? And we've been kind of operating under that assumption here the whole time. And so we actually need to verify that to make sure that we're doing this all the right way, right? So let's just go back here just so I can steal my notations. I just don't feel like writing, honestly. That's why digital inking was like invented for people like me. All right. So these 4 conditions need to be satisfied in order to be a binomial distribution. So therefore, this is binomial distribution. And honestly, probably should have checked this before I even got started with the problem. Because if you look at the Desmos calculator right there in front of you, it says binomial disk. It's like, how do we know to use the binomial distribution? Because these four conditions were satisfied. There's a fixed number of trials. That's the 14 births. Okay, the 14 births. Fixed probability, that's the 50.8 or 0.508. All right. Independent events, that's a tricky one to conceptualize. And so, and you know, the two outcomes is more of a philosophical thing now, but the independent events is kind of a weird one, because if you think about it in the context of a multiple choice question, you know, like if you have four multiple choice questions, each with four choices, independent events means that regardless of what you chose for the first choice, you'll always have all possible choices available for every subsequent choice. So if I selected choice A for question one, I can still choose question A for question two. I'm sorry, choice A for question two, choice A for question three. I can choose it for whatever problem I want. Whereas if it were dependent events, then once I choose choice A, I have one less choice A available. You know, and so that ends up being something that's tricky for folks to kind of wrap their minds around, because, you know, in theory that makes sense, but in a practical sense, it's a little bit different, because, you know, if you take a test and it turns out that you have, you know, like every answer is choice C, you're immediately thinking you did something wrong, right? So there is a little bit of a psychological component to it. Gotcha, thank you. There is a psychological component involved, but that we assume that that's not necessarily the case. All right, so we would just kind of ignore that stuff. The two outcomes, success or failure, we're looking at this, you know, in an academic sense, that the two possible outcomes are male and female. That's not, you know, necessarily the case. And again, it's, you know, I'll say it's above my pay grade to make that determination as to what's what. But for this problem, we're making that assumption. All right. So what do? We figure out, now that we have these four conditions satisfied and we know it's a binomial distribution, it gives us license to use these two formulas. So we know that n is equal to 14. So mu is equal to 14 times the p, which is 0.508. And sigma is equal to the 14 by the 0.508 by the 1 minus 0.508, all under a radical. Okay. So then you could run these numbers. However, I was nice enough to include that stuff in the binomial distribution calculator for you. All right, so mu is equal to NP, put the formula in, put the result in. As long as you type in or put in the 14, the n and the p value, the 14.508 correctly, it'll spit out the NP and the NP times 1 minus p. So in terms of work, there's really not much to show, because you could just submit your Desmos link. So really, for a question like this, you're really just interpreting what the n and p values are, making sure that you know it's a binomial situation, and then Desmos is doing all the work for you. So 0.7112 and about 1.871. Okay, and so from there, what we need to do is actually figure out mu plus or minus 2 sigma. Now, mu plus or minus 2 sigma, as we've kind of worked with repeatedly throughout this semester, it's kind of a recurring theme. That's the same as saying mu minus 2 sigma. It's giving us an interval, and mu plus 2 sigma. All right, so I'm taking that 7.112, subtracting from it 2 times 1.871, then doing the same thing, just adding. Gotta shrinky dinky it a little bit. All right, so I'm gonna change that minus to a plus. Run these numbers, and then I'll have what again is known as the usual interval. All right. So, and you, this one you could just kind of crunch out normally, you know, just typing. So 3.37 on the low end. And on the high end, you know, you can lock it in. You can do a little duplicate, make the minus into a plus. And we get 10.854. And so this is the usual interval or usual range, either way. Interval, no. Usual interval. And so just going back to the original question, is it unusual to get 11 girls among 14 births? So based on that information, it would be. So yes, 11 girls in 14 births would be unusual. I got to tell you, I had to rephrase this question about 10 different times over the years, because no matter how many times I tried to phrase it, it always read as if there was one person giving birth to 14 children. And, you know, as a guy, I definitely, I mean, I think that would probably be at best like cringeworthy. But for all the moms out there, I got to imagine that that would be something in the realm of horrific to imagine. So, so yeah, the whole idea was for me to try to rephrase the problem so that it was clear that it's as if you're walking into a maternity ward in the hospital, and there have been 14 births, you know, from various different mothers. Right. And these are, yeah, it's almost like you're going into the nursery and you see all these little babies, 14 babies, and you're just counting up the pink and the blue blankets. You know, that's what I was going for. All right. So if it didn't read that way, then definitely submit a suggestion for a rephrase. All right. So let me stop that recording.